Good morning, students. I welcome you all for today's session. So, in today's session, we'll be studying regarding thick and thin cylinders. So, this is unit number 2 from module number 2. So, initially, let me start with the definition of a cylinder. So, cylinders are nothing but closed containers known as pressure vessels. Closed containers known as pressure vessels, and these are used to store liquids and compressed air and gases. So these are used to store liquids or compressed air or gases. So it can be either above room temperature or below room temperature. At room temperature, you can store all these things in a normal vessels, but you require these kind of closed containers or cylinders in order to store them either above the ambient temperature or below the ambient temperature. So the typical examples of pressure vessels are water tanks, steam boilers, steam engine cylinders, etc., which can store fluids at high pressures. Right? You can also take the example of your domestic LPG cylinder that also comes under closed containers. The oxygen cylinder, which is used in hospitals, that also comes under the category of closed containers, that is cylinders. So next, we'll just go through the shape of the we'll go through the shape of the closed containers. So these can be either spherical in shape or these can be cylindrical in shape. So these can be either cylindrical in shape or these can be either spherical in shape. So in this particular unit, we'll be mostly studying regarding cylindrical shape and how you are going to classify them into thick and thin cylinders. Right, so the pressure vessels are classified into two groups, as I said earlier, thick and thin cylinders. So it is based on the ratio of wall radius to the wall thickness. So this is important for us. So based on the ratio of wall thickness R to the wall radius R to the wall thickness T. So based on this ratio, we are going to decide whether it is a thick cylinder or a thin cylinder. So for thick vessel, for thick vessel, for thick and thin vessel, how we are going to classify this? This is the criteria. So for thin vessel, if the ratio of R by T is greater than 10, we call it as thin vessel. And if the ratio of R by T is less than or equal to 10, we call it as thick vessel. What is R? R is the wall radius and T is the wall thickness. The ratio decides whether it is a thin vessel or a thick vessel. If it is greater than 10, it is thin vessel. If it is less than 10 or equal to 10, it is thick vessel. Okay. So now we'll be initially starting with thin cylinders. So let us go through what are the stresses coming in cylinders. Stresses coming in cylinders. Right. So to understand that, I have considered a thin cylinder. So I have shown you all the three mutually perpendicular directions x, y, and z. Right, and it is having certain thickness T. It is having certain thickness T. It is having the inner radius as R, and I have considered an element on the upper body of this thin cylinder. I have considered an element on the upper body of this thin cylinder. Right? So that is what I have written here. Consider a cylindrical vessel of inner radius R and wall thickness T containing a fluid under pressure. So I'll assume that there is a fluid here inside this which is flowing or which is stored initially. Right? So it is under certain pressure. Now let us check out what are these stresses. What is sigma 1 and what is sigma 2? How do I call them or how do I represent them? Okay. So the stresses sigma 1 is known as hoop stress. So where is sigma 1? You just check out. This is sigma 1. Sigma 1 is called as hoop stress. So here sigma 1 is called as hoop stress, and sorry, Sigma 1 is called hoop stress. It is also known as circumferential stress, or it is also known as tangential stress. So these are important. Hoop stress, second name for it is circumferential stress, and the third name for the same stress is tangential stress. So hoop stress is denoted by sigma h, circumferential stress by sigma c, tangential stress is denoted by sigma to the subscript t. There are three different names given to the same stress. Right? So that is sigma 1. This is relating to sigma 1. Sigma 1 is called as hoop stress or circumferential stress or tangential stress. Next we'll go to sigma 2, and let us go and check what is sigma 2 and what is the name given to it. Right? So sigma 2 is known as longitudinal stress. Sigma 2 is known as longitudinal stress, and it is denoted by sigma to the subscript L. So L stands for longitudinal. Right? So we got to know that for a thin cylinder, there are two types of stresses which are coming on an element which are considered on its body. So if it is along the x-axis, that is along the centroidal axis of the cylinder, then we call it as longitudinal axis. Right? And if it is on the surface, then we call it as hoop stress, or if it is along the circumference, we call it as hoop stress. If it is along the periphery, we call it as hoop stress. Right? So there are different terminologies which I am using: periphery, circumference, along the surface, all are same. Those are used to represent circumferential stresses. Right, now next we'll be going for a derivation. So derivation of expression for hoop stress. So in order to derive an expression for hoop stress, what I have done, I have considered a cylinder. I have considered a cylinder. So this is a cylinder what I have considered. Right. Consider a cylinder subjected to an internal pressure P. So I have shown the internal pressure P. There is some fluid stored into this, and having an internal diameter D as shown in the figure. Right. So the internal diameter, that is from this point to this point, internal diameter is D. Right. So internal diameter is D. I have shown it here, and it is having certain thickness T, and the length is L. Length is L. Right. Now, in this, there is something called as bursting stress or bursting force which is coming into picture. Now, what is this? Let us check out. Now, what I'll do, in this direction, if I just take a section, in the direction shown by this yellow color cut section, so the resulting figure will be of this type. Now, why I have taken the section here in this direction? I am assuming that because of the fluid pressure which is stored inside, the cylinder will burst. Along this direction. The cylinder will burst along this direction. I have shown here. Right? If the cylinder is going to burst along this direction, so this will be the cut section. Right? So there are two forces which are coming into picture. One will be the bursting force. Which will be caused by this one, the fluid which is present here. It will be trying to burst the cylinder in this direction. Right? The fluid which is present here inside the cylinder will be trying to push the cylinder or burst the cylinder in this direction. So that I call it as bursting force. And we know that force is stress into area. And that is the reason FB I call it as bursting force, and it is given by, in this particular case, for bursting force, you are having pressure which is acting here. So pressure is P. I've shown it here. Pressure is P. And what is the area? Area is this entire inner part. Area is this entire inner part. This part. Okay, so this entire inner part is the area. Now, same thing if you just check it here in this cut section. Please note my words, very important. In this cut section, if you just observe this, now this area, whatever I am marking here, so it will be projected area, and from, you just observe it from the top view, it will be something like this, right? So this will be your length L, right? So this will be your length L, and this will be your diameter. Just to make you understand, this is not an accurate dimension figure, sorry for that. But if you just observe this area which I have marked here with green color, from the top view, it will be a rectangle. We call it as projected area. We call it as projected area, right? So, or you can also call it as exposed area, which is exposed to the fluid. So stress, we got to know, that is, in this case it is pressure P, because pressure P is trying to burst the cylinder. Next, for area, you need to take the projected area. So what is the area of rectangle? It is length into breadth. In this case, length is L and breadth is D. So I have taken it as D into L. So bursting force FB is equal to P into D into L. Right. Next, you know that for every action there will be an equal and opposite reaction. For every action there will be equal and opposite reaction. So there will be some resisting force set up in the cylinder. There will be some resisting force set up in the cylinder. So that resisting force is given by, once again, stress into area. That resistance is given by circumferential stress. Circumferential stress. So I told you what is circumferential stress. It will be always acting along the circumference. You can just check out. So this is the circumference, right? So this is the circumference. So on the cut section, you can just observe these red colored stresses. So these are nothing but circumferential stresses, right? So stress is sigma c, which is circumferential stress. And how you are going to calculate the area? In order to calculate area, you just concentrate on these hatched rectangles. So in order to calculate the area, you should know the length of this hatched rectangle. So from this point to this point, we are just observing what is the length over here. So length is nothing but L. Okay, so this length is L because it is the length of the cylinder. So L into this thickness here, the thickness of this hatched section is P. So L into P is the area on which the circumferential stress is acting. But it is not only acting here, but it is also acting on this side. It is acting on this side as well as this side. So it is 2 times L into P. That is what I have written here. Area is 2 times L into P. 2 times L into P. Right? So you can just check out here. You are having thickness T. Right? So this distance is L. You agree with me? This distance is L. This is T. So what is the area of this rectangle? Area of the rectangle, hatched rectangle, is L into T. Right? But there are two hatched rectangles where this sigma c is acting, so it should be multiplied by 2. So the area where sigma c is acting is 2 into L into 2 into L into T. Right? So I have written here 2 into L into T. So next, for equilibrium, FB should be equal to FR, that is bursting force should be equal to resisting force, and that is the reason if you just resolve this and simplify things, what is happening, L and L is getting cancelled. So sigma C will be equal to PD by 2T. So this is the expression for circumferential stress or hoop stress or tangential stress. Right now, similarly, we'll be going for calculation or derivation of longitudinal stress. You can just check it here. So in this, what we are trying to do here is FB is the force which is causing the bursting. In this particular case, what I am assuming is, in this particular case, what I am assuming here is, I am taking the section like this. I am taking the section like this here at this particular point, right? So if you cut it like this, so what are the stresses which are developed in the cylinder? Now the cylinder will be bursting in the direction opposite to what we have taken previously, right? Previously the section was taken horizontal, now the section is taken vertical, right? Now the section is taken vertical. So here also you are having the bursting forces and the resisting forces. So in this inner part, you are having the fluid over here. So here you'll be having the fluid and it is having certain thickness T. This cylinder is having certain thickness T. Now, if the cylinder has to burst in this particular case, so we know that bursting force is equal to stress into area, right? So let us go ahead and check out what is the bursting force. So you can just check out here. Bursting force is internal pressure into cross-sectional area of the cylinder. Now this is important in this particular case when you are taking the vertical section. When you are taking the vertical section, your area will be cross-sectional area of the cylinder. Area will be cross-section area of the cylinder. And why? Because you are cutting the cylinder vertically and the area which you will be exposed in this case will be cross-sectional area. So bursting force here will be given by the internal pressure into the cross-sectional area of the cylinder. So what is the cross-sectional area of the cylinder? Cross-sectional area of the cylinder is pi by 4 d square, pi by 4 d square, where d is internal diameter of the cylinder, right? So next, there will be once again some resistance. So that resistance you can just check out. It is shown by this term FL, right? Longitudinal force is going to resist the bursting of cylinder in this case. So where this longitudinal force is acting, it is acting on this hatched area. What is this hatched area? Hatched area is pi into d, pi into d into t. So this hatched area where this FL is acting, so it is pi into d. Pi into d is nothing but circumference into thickness t. So this is the area where FL is acting, right? So how you calculate the resisting force? So the resisting force is given by longitudinal stress sigma L, longitudinal stress sigma L into pi into d into t. So once again, for equilibrium, your resisting force should be equal to the bursting force, right? So resisting force should be equal to the bursting force. So in that case, when you equate them, I'll be getting an expression for sigma L, which is PD by 4T. PD by 4T. How you got this? So sigma and pi and pi you cancel it. 1D and 1D is going to cancel here. So sigma L is equal to PD divided by 4T. You get this expression, and this is the expression for longitudinal stress. Right. So now the last part, I'll be coming to the last part of today's session. So one more important thing, if you compare the equations 1 and 2, where is your equation 1? So this is equation 1. Sigma c is equal to PD by 2T, right? And the next equation 2, sigma L is equal to PD by 4T. So if you just try to correlate using equation 1 and equation 2, right? So sigma c is equal to PD by 2T. This was your equation 1. We just try to correlate these two equations. We'll be getting sigma c is equal to sigma L divided by 2, and that is the relation between circumferential stress and longitudinal stress. Right? So the maximum shear stress is given by the formula sigma c minus sigma L divided by 2. So this is also important because we require the calculation of shear stress. So it is given by sigma c minus sigma L divided by 2. Right. So that's it for today's session. Have a good day. Take care.